Hello students, welcome to grade 12 chemistry revision lesson on the half-life of a reaction. At the end of this lesson, you will be able to define half-life, calculate the half-lives of zero order, first order and second order reaction from experimental data. Identify the rate determining steps from a given reaction. Define reaction mechanism. Students, if you are ready, then we will get started. The half-life of a reaction. The half-life of a reaction is time required for the concentration of the reactant to reach half its initial concentration. Half-life time of a reaction is denoted by the symbol T half. T half is time required for concentration of a reactant to reach half its initial concentration. The half-life of a reaction is designated by the symbol T half. Half-life of a first order reaction. We said an integrated rate equation for the order reaction is this: log initial concentration A naught divided by concentration of M at any time t equal Kt divided by 2.303. When concentration of M is half its initial concentration, the time is T half. Therefore, log initial concentration A naught divided by concentration of M is half its initial concentration A naught divided by 2 equal K times T become T half divided by 2.303. Now this is the same as A naught will be cancelled by A naught. Log 2.303 times log 2 divided by K equal T half. But log 2 is 0.3. 0.3 times 2.303 divided by K is 0.693 divided by K. Therefore, the half-life time for a first order reaction is 0.693 divided by K, where K is a rate constant. Half-life of a zero order reaction. An integrated rate equation for the order reaction is this: concentration of M at any time t equal minus Kt plus initial concentration A naught. We can write this as concentration of M at any time t minus A naught equal minus K times T. When concentration of M is half its initial concentration, concentration of A naught divided by 2 minus A naught equal minus K times the time become half-life time, T half. From this T half equal A naught divided by 2 minus A naught is minus A naught divided by 2. Therefore, T half equal A naught initial concentration A naught divided by 2 times K. This is half-life time for zero order reaction. T half equal initial concentration divided by 2K. For example, what is the half-life of dinitrogen pentoxide if it decomposes with a rate constant of 5.7 times 10 raised to minus 4 per second? How do you know decomposition is first order? Note that the units of rate constants for first order reaction is per second. Therefore, decomposition of dinitrogen pentoxide is a first order reaction. Now the lifetime for a first order reaction is this: T half equal 0.693 divided by K. T half equal 0.693 divided by K. The rate constant K is 5.7 times 10 to the power of minus 4 per second equal 1200 seconds, which is 20 minutes. 20 minutes. This is the half-life time for the decomposition of dinitrogen pentoxide with rate constant 5.7 times 10 to the power of minus 4 per second. Half-life of a second order reaction. An integrated rate equation for a second order reaction is this: 1 over concentration of A at any time t minus 1 over initial concentration of M equal K times T. When concentration of M is half its initial concentration of A naught divided by 2. This equation is the same as 1 over A naught divided by 2 minus 1 over A naught equal K times T half. Therefore, the half-life time for a second order reaction is 1 over K times initial concentration A naught. This is half-life time for a second order reaction. For example, the rate constant for a second order reaction is this: 2m gives beam is 0.80 per molar per second. Chem rate constant for the second order reaction is 0.80 per molar per second. The initial concentration M, the initial concentration A naught equal initial concentration is 0.086 molar. Calculate the concentration of the final concentration after 22 seconds. An integrated rate equation for a second order reaction is this: 1 over concentration of M at any time t equal Kt plus 1 over initial concentration A naught. 1 over concentration of M at any time t equal Chem, rate constant having value 0.80 per molar per second times t is 22 seconds plus 1 over initial concentration A naught is 0.086 molar, 0.086 molar. Now, concentration of M after 22 seconds become concentration of M after 22 seconds equal 0.034 molar, 0.034 molar. B, calculate the half-life when concentration of A equals 0.072 molar. The half-life time of a second order reaction is this: T half equal 1 over K times concentration of A naught. 1 over K times concentration of A naught. T half equal 1 over the rate constant Chem is 0.80 per molar per second times initial concentration is 0.072 molar. Now T half, the half-life time for this reaction is 17.4 seconds. Reaction mechanism. The sequence of events that describes the actual process by which reactants become product is called the reaction mechanism. Some reactions occur in one step, while other reactions occur in multi-step. Therefore, reactions may occur all at once or through several discrete steps. Each of these processes is known as an elementary reaction. For a reaction that takes place in multi-steps, elementary reactions add up to give the overall reaction. The sequence of elementary steps that leads to product formation is the reaction mechanism. Elementary steps and molecularity. Elementary step is any process that occurs in a single step. Molecularity Molecularity is defined as it is the minimum number of reacting particles, reacting species. These particles can be ions, molecules, or atoms that can react, that can collide, that can contact with each other to form a desired product. Therefore, molecularity of a reaction can be unimolecular if there is only one reacting species, unimolecular, one molecule in the elementary step. For example, A2 product, there is only one reacting species. Now this is unimolecular. Bimolecular, when two reacting species are there. Now the elementary step, elementary reaction is bimolecular. For example, A plus M, two colliding species, two reacting species are there. A plus A to form product. Thermolecular, three molecules in the elementary step. For example, A plus M to form product. There are three reacting species that form a product. Thermolecular is rare. Colliding of three species is rare. Rate's law for unimolecular. Rates equal K times concentration of A to the power 2. Therefore, the overall order for unimolecular reaction is the same as molecularity of the reaction. Is unimolecular, one reacting species, its order is 1. For bimolecular, the overall order is 2. For thermolecular, the overall order is 3, the same as molecularity of the elementary step, elementary reaction. Rates determining step. For a reaction having multi-step, the slowest step is rate determining step. The slowest step in a reaction mechanism leading the formation of a product is called the rate determining or rate limiting step. Overall rate equal the rate of the slowest step. For example, the rate law for the reaction, 2NO2 gas plus F2 gas to form 2NO2F gas can be thought of as occurring in two elementary steps. As we said, for a reaction having multi-steps, the slowest step is rate determining step. Therefore, rates of this reaction, rates equal K times concentration of NO2 to the power 1 times concentration of F2, NO2 times concentration of F2. Now, step 1 is the rate determining step, because step 1 is the slow step. F is the intermediate. Intermediates are chemical species that occur as a product in one elementary reaction and act as a reactant in the other elementary reaction. If you look at this reaction, F here appear as a product. Here act as a reactant. Intermediates do not appear in the overall reaction. As we said, elementary reactions add up to give overall reaction. Therefore, intermediates do not appear in the rate law expression. F is the intermediate because it does not appear in the rate law. Now, rates of this reaction is K times concentration of NO2 times concentration of F2 is the rate law for this reaction. Example, look at this reaction. This is overall reaction of these elementary reactions. Elementary reaction add up to give overall reaction. You see, N2O2, this will be cancelled by this. NO plus NO is 2NO, 2NO plus O2, form 2NO2. The slowest step is the rate determining step. Therefore, rate of this reaction is rate equal K times concentration of N2O2 times concentration of O2. But N2O2 is an intermediate. Intermediates do not appear in the rate law expression. Now, step 1. This elementary reaction is equilibrium reaction. A reaction is said to be at equilibrium if and only if forward rates are forward equal the reverse rates or reverse. Now, the forward rates depend on concentration of the reactant. Forward rate is K forward times concentration of NO to the power 2, concentration of NO to the power 2 equal reverse rates depend on concentration of N2O2. K reverse times concentration of N2O2. Now solving for concentration of N2O2. Concentration of N2O2 equal K forward divided by K reverse times concentration of NO to the power 2. As we said, intermediates do not appear in the rate law expression. You have to eliminate it. Now, rates equal K times concentration of N2O2 is K forward divided by K reverse times concentration of NO to the power 2, concentration of NO to the power 2 times concentration of O2. Rates are equal. K is constant. K forward divided by K reverse. Again, constant divided by constant gives you another constant. Now, constant times constant gives the overall constant. The reaction constant, K overall times concentration of NO to the power 2 times concentration of O2. Now, this is the rate law for this reaction. Students, let us try this exercise so that you can practice what you have just learned. The reaction NO2 gas plus CO gas gives NO gas plus carbon dioxide gas can be thought of as occurring in 2 elementary steps. Elementary reaction 1 is the slow step. Elementary reaction 2 is fast. Now, elementary reactions add up to give the overall reaction. Identifying the rate determining step and determine the molecularity of this reaction. You have 2 minutes. Welcome back again, students. How did you do it? Good. Identifying the rate determining step. As we said, the slowest step is rate determining step. Therefore, step 1 is rate determining step. Step 1 is rate determining step. Determining step. Determine the molecularity of this reaction. The molecularity of this reaction is two reacting species, NO2, NO2. Therefore, the reaction is bimolecular. Students, in our today's lesson, we discussed the half-lifetimes of reactions. Half-lifetime is time required for the concentration of a reactant to reach half its initial concentration. We have seen half-lifetime for zero-order reaction, half-lifetime for first-order reaction, half-lifetime for second-order reaction. We discussed reaction mechanism, the sequence of events that describe the actual process by which reactants become product is called a reaction mechanism. This brings us to the end of our today's lesson. Until next time, goodbye.